Right, the Drake equation. All right, so this is our highly unscientific science equation. And what it is telling us is the number of advanced civilizations that we can detect. Right, so this doesn't mean that they're out there. This just means the ones that we can probably contact. Right? So, um, how the key variables here, and the ones that we roughly know that are pretty good, are the rate of formation of sun-like stars. We know that's roughly about 10 new stars are born anywhere in the universe, we think. And given our current data set, we think about a third of all stars probably have some kind of planetary system around them. The thing we don't know is, how many of those are Earth-like planets per system. It's starting to look like about every solar system we find has something that has an Earth-like planet. And then we've got some variables that we just really don't know. We've got um, F of L, which is the fraction of which life emerges, right? We don't know how life emerged here on Earth, so this is a complete guess. Fractions that evolve intelligence life, that's also a guess. Fraction that can communicate, that means that they develop enough technology such that they can share it, and the lifetime of their civilization, right? And this is an interesting one which we're going to talk about here shortly. So let's going to explore a few of these. So N of E is basically the number of planets times the fraction of stars that are suitable. That's where that number comes from. Okay. And so that's the best guess that we have for that number. So that's the third term in here. So that's the one that is, of the guesses, the least guessy one. Um, and there's some optimism that are out there. Carl Sagan was highly optimistic back in the day that each solar system could potentially have up to 3 Earth-like planets, right? For instance, he goes, if Venus had less clouds, we've seen that if it had oceans, it was within the habitable zone of the sun. It's right on the fringe now, if not a little inside the habitable zone, so it would be pretty toasty on Venus. If Mars had a thicker atmosphere, it would support life, and eventually Mars is going to be back in the habitable zone. And what if we didn't need water? What if something else could be a backbone of life formation that we don't quite understand or know yet, because all of our assumptions about life is grounded on the fact that you have water. Okay, so let's talk about what we're all made out of. Right? Elvis, dinosaurs, cats, jellyfish, viruses, you name it. So what are we made out of? Well, at least right now on Earth, almost everything is made out of 4 basic elements. And about 95% of all the mass on the planet is made out of combinations of hydrogen, oxygen, carbon, and nitrogen. Which means that if we don't have those 4, it is highly unlikely that we will end up with life. So this is commonly referred to the HOCN set of elements. Right? We're going to see how important those things are here. We do have some trace elements that are also important because, we can't live with just those 4 because we know we take vitamins and minerals. And so those are things that include sulfur, magnesium, chlorine, potassium, sodium, right? All of those things end up being very important. But despite that, these are micro elements in essence because they only made up about 1% of all living organisms, but they're about the same concentration as everywhere. But what's interesting is that the oceans have about 1% of this combination of elements too, which gives us a strong clue that maybe life started there. Because on land, it's a little bit different, is that you have hot pockets of things, right? You have a sulfur mine, right? So you have concentrations of it, where it's pretty uniform throughout the oceans. So it turns out that we really kind of are special stuff, despite what the X-Files would have us to believe back in the day. So why is it that HOCN are critical? So why not, let's say, lithium, which is also a pretty abundant element? What about helium? Right, helium's highly. Why aren't we made out of helium? So why these 4? So let's talk about that. The critical one in that list is carbon. because carbon is unique, is that carbon is one of the elements that has the ability to create long chains of molecules, and that means that it becomes very highly stable because it can bond with 4 bonds, which means that you can attach multiple elements to different components of the carbon atom, and that makes it look like an inert gas or noble gas, which means it's very, very stable. That's why there's an entire field of chemistry called organic chemistry, because it's basically devoted to carbon, because carbon is very, very important. Because once you get 4 electrons, right, 1, 2, 3, 4, carbon ends up looking like the shells of neon, and neon is incredibly stable. This is why boron doesn't work so well, right, is that it doesn't have the nice way of being able to end up looking like neon, because its outer shell isn't like carbon. Now, notice this row here. Carbon could be replaced by silicon, because silicon has similar properties to carbon. It's not as abundant as carbon. Carbon is very abundant. It's everywhere. But silicon could exactly have the same properties. So you could potentially run into silicon life-based forms, right? The chemistry would be very different, and it would probably react very differently to things, but same idea. Then once you get down to germanium, it's too many electrons for germanium, but life we suspect will exist out of carbon and silicon. The germanium atom isn't quite as stable as carbon and silicon because the outer electrons tend to get easily stripped away on germanium. So our carbon bond, right, it's got 2 electrons on its inner part, but the second shell could be filled by 8, but it's only got 4, which means that it can attach to 4 elements, which makes it immensely useful, because some of these models that you've seen before that work pretty well, like CH4, that's methane, right? That's what we use to create fire and heat homes and things like that. And what's also interesting about carbon is it tends to be a covalent bonding mechanism, because it means it shares its electrons equally, which is also what makes them very stable bonds. Okay? And you get these long chains, right? So you get methane, you get ethane, you get hexane, right? You get isooctane, which is the foundation of gasoline, right? You get cyclohexane, which is nerve gas, because carbon has this unique ability. And you also get really important chemical compounds like insulin. Notice it's got 254 carbons, right? And it's got 377 hydrogens, 65 nitrogens, 76 oxygens, and 6 sulfurs. But notice that carbon, hydrogen, nitrogen, oxygen are the core components of what makes up this hormone that allows us to digest our food. Right? Because carbon is very important. And carbon creates all sorts of different shapes. And I always like this picture because when you take a look at cocaine, right, and LSD, notice they're a little similar in nature, but take a look down here at testosterone, right? It's not that far removed from LSD, all right? Ibuprofen basically has a benzene carbon ring, all right? And notice it's not that significantly different from Tylenol. So once you have one molecule and you know what it does, that you can begin to think about how you would modify and add this. And this is what pharmaceutical companies do all the time, right? They're trying to manipulate this and being able to understand how the bonds would react and how the chemistry reacts. So where did all of this stuff come from, right? Where did carbon, hydrogen, oxygen, and nitrogen come from? Well, early in the universe, we're going to learn that the universe basically only was made up of hydrogen and helium when we started. So where did all of this stuff come from? It came from stars where they blew up. And what we're going to do next is we're going to tackle how stars operate and how we end up getting all this carbon, hydrogen, nitrogen, and oxygen.